All right. Today we go into a little bit deeper than usual into questions of stability. And when I say we go a little bit deeper than usual, here's what I mean. Normally, throughout the whole course, we were discussing linear systems. There was a very good reason why we chose to discuss only linear systems. The theory for linear systems is polished. It is very good. It is very easy to work with. And I would say a very big portion of control that is done anywhere, practical control, deal with either instruments from linear control or directly uses linear control. So a lot of stuff that people use comes directly from this field, right? So that's why we were limiting ourselves. We were going to linear control. We wanted to understand everything there was about it. We wanted to see how well organized the theory is, so we can have a complete picture. Later in other courses, you'll be able to explore nonlinear control and other things like that, right? But today we make an exception. Today we are going to look into one tool that is the foundation for nonlinear control. That is Lyapunov theory. The reason I want to bring it up is because this fundamental is so versatile and powerful that it can also serve as a foundation for some of the linear control techniques. In fact, there's a whole field of linear control techniques which are essentially based on this theory. So while today we are going to explore something that would be foundational for a nonlinear control course, it is also going to be useful for a linear control course. And in general, it is one of those things that is very good to know. All right, so Lyapunov theory, one of the most celebrated theories in the history of control. All right, good. Let's get into it. So we'll start right off with a definition. We'll find new criteria for stability. You remember previously we had eigenvalue criteria. The criteria was if you have negative real parts of the eigenvalues, strictly negative, you are asymptotically stable for a linear system, right? If you have non-positive eigenvalues, you are marginally stable. If you have at least one positive real part of eigenvalue, you are unstable. That was how criteria worked for linear systems. Now, general criteria for general nonlinear systems. So consider autonomous dynamic system. Remember, always we are thinking about autonomous systems, because if you have input to the system, it is very hard to explain what you mean by stability. So we are thinking about autonomous systems, systems which depend on the current state of the system, where derivative depends on the state, on nothing else. Right? So consider autonomous system. It will be asymptotically stable. So the solution will converge. Small derivations from the solution would converge to the solution. Or if zero is a solution, then every trajectories will converge to zero. Right? If there exists a scalar function v, which is positive everywhere, except at zero. So it is positive everywhere, but at zero, it is equal to zero. And its time derivative, right? Time derivative is negative everywhere, except at zero, where it is zero. So the function, you can think of it as some kind of cup, like a ball. It grows out of, like at zero, it is zero. Everywhere else, it is bigger, right? Or positive everywhere. And not only that, but if you're going to follow a trajectory on this ball, it will only go down. That is what it means for the time derivative to be zero. The trajectory will only go down, because you can imagine the function itself is like a ball. We're saying the derivative is negative, meaning that as time goes on, our point on this ball will only slide down. Doesn't matter if it slides down like this or somehow else. It has to slide down, right? That is the idea. And then the system is asymptotically stable. Now, there is a conceptual problem here, which we need to address before we go anywhere. So conceptual problem is something like this. What does it mean for this function to have a time derivative? Because v of x, let's say it is x squared, we call it x squared. So it's actual like ball, paraboloid. What does it mean for it to be to have a time derivative? Well, what we actually mean is that x itself behaves according to this expression. So x itself behaves the way the dynamics dictates, right? So the given current x, you know where the next x will be located because of the dynamics. So this equation describes how x will go from current x to the next x. This has nothing to do with v. It is just like how dynamics works. We call it vector field. In differential geometry, we call it vector field. So basically, for any x, there will be a direction where it points. It is convenient to think of it as in 2D case, as you can imagine here is a two-dimensional space. And at any point on this space, there will be a vector. So x here would have a derivative like this. X here will have a derivative like this. X here, derivative like this, right? Right. At any point, you can point out where exactly the derivative will go, right? That is the idea of a vector field. Like you pick a point, you know what derivative will be like, right? That is, and when we say derivative of v, so v dot is negative, what we mean is x will follow naturally this flow that is described by this, what do you call it, dynamics, this vector field. It will naturally follow it. But if this is true, then while naturally following, it will always go downhill. So if you can imagine your function having those what do we call them? You remember in topology you would study how the elevation of the terrain is organized, right? So you can draw a line that connects elements of the same height, right? Anyone remembers the term for this?
Геодезические линии.
Yeah, geodesically. No, but there should be a term for equal height kind of contours. In plotting, we call it contour plot, right? But anyway, contours of equal elevation, right? So you can imagine what I mean is like here's the lowest point of the function. Here's the circle of higher points. Here's even higher points. Here's maybe even higher points. Like the function somehow goes down in this direction. So what I'm trying to say is, if the function is stable, we can prove it by looking at the behavior of x, which would, if this is true, would inevitably be drawn towards lower and lower contours, and eventually will fall into point v equals to 0, right? So that is the whole idea. X, its behavior depends only on x dot equals f of x, right? But if you look at this function, the way x will trace trajectory on this function would be only going downstairs, only going downhill, eventually reaching this point v of x equal to 0. In which point it will stop because derivative of this function at this point is 0. So it will be drawn towards the lowest point and will stay there. That is the behavior we are looking for, and that behavior can prove stability, right? I think this is a little bit abstract and it is always difficult to understand. But think of it this way. If you are standing somewhere, let's say, in a valley, and you can only go down, like every step you take, your elevation has to decrease, right? Your elevation has to decrease, no matter which step you take. Like you're not allowed to make a step which does not decrease your elevation. So you cannot go around in a circle because your elevation at the end of the circle will be the same as in the beginning. This is not allowed. Each step has to put you down, like 1 centimeter, 1 millimeter, but down. You cannot go back up, right? You can imagine if this is your rule, no matter what you do, after some number of steps, you will reach the bottom of the valley. Like you will reach the lowest point, simply because you cannot help it. You cannot ever sit in some kind of circle which does not go even further down, right? If you had like a perfect road which sort of like circles the valley without going up or down, this road would violate this condition because each step would not bring you down. It would keep you on the same elevation. So even that trick won't work. You always have to go down. So you would reach the bottom of the valley, no matter what you do. And you can imagine that if this is your behavior, that means that your trajectory is stable. As in, you're not going to leave this valley. You're not going to go somewhere towards the horizon. Because the lowest point is at the bottom of the valley. And that is where you're going to get, like, that is where your steps will have to lead you, right? So that's the idea. That is the idea. That is more of a visual explanation. That is not so much mathematical explanation. But I think for you, it is important to get stuff like visual understanding of this first. There is a mathematical proof for all of this and in plenty of textbooks, so we don't have to do it here. What I really want you to is to just have a visual image of what is going on. All right, good, good. Now, let us look at other stability criterion. So the same exact situation, but we allow the function, the derivative of the function v dot, to be non-positive. That proves marginal stability. So that's exactly the situation where you have a rod which does not go down or up. So if you can follow this function somehow without going up or down, then it is marginally stable. You're still not going to go off into infinity somewhere. You're not going to be unstable, but you're not asymptotically stable. So you're not converging anywhere necessarily. All right. So this function, v of x, is called Lyapunov function. Right? It's called a Lyapunov function. Now, all of this was abstract, but we are going to make it concrete now. But let's just study some examples. So consider this very simple system. We studied it already plenty of times. You know how to deal with it eigenvalue-wise. You can just prove that eigenvalue of the system is -1. -1 is, well, real part is negative, so asymptotically stable. Right? Or you can even write a solution to it, and you can prove that solution converges to 0. But now let's do it using Lyapunov theory. So Lyapunov function candidate. Candidate is, the reason we call it candidate is because we did not prove anything yet. So we just propose a function which hopefully will have properties that we described in the previous slide. So positive everywhere except 0, derivative negative everywhere except 0. If we can prove those properties, it is a Lyapunov function, and we proven stability of the system. If we could not prove those properties, it was a failed candidate. All right. So Lyapunov function candidate, x squared bigger than 0. Right. We can instantly see that x squared is bigger than 0 for any x which is not 0. At 0, it is exactly 0. So already we satisfied the criteria v positive everywhere except at 0. Next, let's find its time derivative. The time derivative of x squared will be, it is a derivative of a chain rule, right? We apply chain rule. So first we take derivative of x squared of the square function. That would give us 2x, right? Next, we take derivative of x. X itself is a function of time. So dx dt would be x dot, right? Let me just remind you what we just did, right? We take derivative of a function of x. And so it is basically df dx times dx dt, chain rule, right? First, we take derivative of a function with respect to the argument x. Then we take the derivative with respect to the argument of the argument with respect to time. So that's what we did here. Dx squared dx is 2x. Dx dt is x dot. So 2x times x dot. Now, we can notice that x dot is actually equal to minus x, right? So we can substitute this here. And what we'll get is 2x times minus x. When we open the brackets, what we get is minus x squared. So 2 times x minus x squared. And this happens to be negative everywhere except at 0. So this is strictly negative everywhere, but it is 0 at 0. So we have satisfied both conditions of Lyapunov criteria, and we have proven that this is a stable system using Lyapunov theory.
So this criteria is about if we can find any function that satisfies it, so this system is definitely stable. Like
Yes.
this?
Yes. So there isn't like one Lyapunov function. You can find infinitely many. In fact, if you instead of x squared, we take 1/2 of x squared, would work just as well.
Fine, thank you.
So there are infinitely many Lyapunov functions, and finding them is art. There is automated ways to search for Lyapunov functions. And that is a big research topic right now. Like a lot of work is being done in automating search for Lyapunov functions because it will be very practical, very useful to be instantly able to produce Lyapunov function given a dynamical system. All right, good. You'll probably learn about it in a nonlinear control course if you take one, I think. Probably. All right. So this we've proven. Any more questions about this one before we go to the next example? Okay, I think not. Then next example. So consider a system q double dot equals f of q dot, right? So q double dot, second derivative of q, is a function of positional variables and velocity variables, right? Classical mechanical system. In particular, it is minus q dot minus sine of q. So you can think of it as something like a pendulum with a damping. Right. Let's prove stability of this pendulum. So again, as before, we propose Lyapunov function candidate. This time we will choose energy of the system. We know that energy naturally is supposed to decrease, right? Like energy is supposed to go down always. So sounds like a good candidate. So let's just use energy. So this is the kinetic energy of the system, 1/2 of q squared, q dot squared. This is potential energy of the system, 1 minus or cosine q. The sum is always bigger than 0. Why? Well, because this part here is strictly positive, or 0. This part here is strictly positive because cosine cannot be bigger than 1. So overall, it is strictly positive. It can attain 0 if q is equal to 0, or q dot equal to 0, and q is equal to 0 as well. So at the point 0, it is exactly 0. So satisfies the first part of the criteria. Next, we will try to find derivative of this function. So let us just differentiate with respect to time this whole thing. Right? Okay, what do we do? Well, first, we differentiate with respect to time, with respect to q dot, this guy. So it's 1/2 q dot squared with respect to q dot. It will be 1/2 times 2 q dot, right? We differentiated partial f, partial q dot. So we get q dot. But remember chain rule, so you have to multiply it by dq dot dt. So differentiation works, again, just to remind you. Df, if you want to take derivative of f of x, you take df dx, dx dt, right? Multiply with each other. So df dx, in this case, it is 1/2 q dot squared. Oh, sorry, differentiate with respect to q dot. And then q dot differentiate with respect to c. That gives us q double dot. Here. Next, we differentiate 1. It gives us nothing. Derivative of 1 with respect to 0, t is 0. Next, we take derivative of minus cosine q. So minus cosine q, differentiate with respect to q, it gives us sine q, right? So cosine minus cosine with respect to q is sine. But remember, dq dt, right? df dq, dq dt. So dq dt is q dot. Now, what we can do next is we can put q out of the brackets. And in the brackets, we leave minus, yeah, in the brackets, we would have this, but let's also replace, remember to replace q double dot with minus q minus sine q, right? That's what q double dot is. So we replace it here. Yeah, okay, let's not even take this q out of the bracket, sorry, my bad. One more time. We take this expression here, q, q double dot becomes this, right? So here it is. Plus the expression here, sine q times q dot, sine q times q dot. What we see next is that q minus sine minus sine q times minus sine q, again q dot times sine q, they cancel. So this is the same expression but with opposite signs, so they cancel. Q dot times minus sine q, q dot times plus sine q, They cancel. The only thing that is left is this expression here. So minus q squared. That was clear, the derivation. Yeah, hopefully. I think the math is very simple. Describing it with words is very complicated because of all those partial, q dot, etc. The language does not really facilitate the communication, but the mathematics, I think, is quite clear. So your time derivative becomes minus q dot squared, which is less than 0. You can see that this is going to be less than 0 for any q dot. But here is a big difference from the previous example. It is going to be equal to 0 for any q dot that is equal to 0 and for any q whatsoever. So it is not only 0 at the point 0. It is 0 at the point where this guy is 0, while this guy is anything. So 100 and 0, 20 and 0, minus 5 and 0. So for any position and 0 velocity, this Lyapunov function obtains 0 as a derivative. Big problem. Does not satisfy asymptotic stability criterion. All we were able to prove was marginal stability. So we were able to prove marginal stability, not asymptotic stability. But do you think the system actually is marginally stable or asymptotically stable? Can someone tell me?
Definitely asymptotically,
Why?
because it's pendulum with dissipation, it cannot blow up to the infinity energy.
That is marginal stability, the fact that it cannot blow up. But I'm asking if it is marginally or asymptotically stable.
It is asymptotically stable because if time tends to infinity, then the dissipation of energy will tend the energy to the 0.
Correct. Yes, correct. That's true. So somehow the fact that we were not able to prove asymptotic stability here is a problem of the theory, not the problem of the pendulum. Okay, let's fix that. Let's fix it. Now we would need second part of the theory for discussing this type of problems. And this part of the theory is almost always necessary. Somehow it's like just absolutely important. It's called LaSalle invariance principle. What it tells us is this. Dynamical system, autonomous system, right? X dot equals to f of x will be asymptotically stable if we find positive Lyapunov function, given, of course, 0 at 0, whose time derivative is non-positive. Apologies for what is written here. Time derivative is non-positive as long as the set of x which contain all 0 derivatives of the Lyapunov function does not contain non-linear, non-trivial trajectories. All right. So first of all, what is a trivial trajectory? Trivial trajectory is very simply x equal to 0. So any other trajectory is considered non-trivial. So what now the game became 1 degree more complicated. Previously, our game was to find function v everywhere positive except at 0, derivative everywhere negative except at 0. Now game changes. Now we are allowed to find a function everywhere positive except 0, everywhere non-positive, derivative everywhere non-positive, right? So it doesn't have to be negative everywhere. Non-positive is enough. But if it has zero derivatives, also like sets over of values of x, the derivative is going to is zero. This set should not contain a trajectory other than a trivial trajectory. So we cannot allow any solution to this equation. Trajectory, remember, is a solution to this equation. We cannot allow any solution to this equation to sit inside this set. Now, this set, to some of you, I think it might sound unclear. Like, what are we talking about? What is this set? Remember my analogy previously about the road that goes around this valley without going up or down? That is the set. That is a LaSalle set that we are discussing here. So a road that does not go up or down, just sits somewhere equal elevation. If you follow this road, you are not going to descend or ascend. So your time derivative is zero. The criterion says that such roads should not contain valid solutions. So it says that X will never follow such a road because it contradicts the dynamics. So if there exists a solution that would follow this road, then you did not prove anything. So all you need to do is to show that there are no such solutions. Hopefully the visual idea was somehow helpful. All right, let's just apply it and let's see how it works. But before we apply, just one additional piece. So there is a local version of the principle. Local version. Local basically means we are not going to discuss the whole number line, like Rn, like all numbers. We're going to discuss some region. We'll call it D, neighborhood D, right? We'll only discuss that, right? And the principle becomes different in the following sense. So consider an autonomous system. We call it asymptotically stable in the neighborhood, right? So locally stable. So it's going to be stable as long as you are starting from in this neighborhood. Neighborhood of the origin, in this case, that's how I wrote it. If we can find same positive Lyapunov function, so 0 is 0, whose time derivative is non-positive, and this set of x where the derivative is 0, at least the part of it which lies inside the neighborhood, right? So this is what this means, intersection sign. So the part of this set that lies inside the neighborhood, it does not contain non-trivial trajectories. So we're not asking for the everywhere. We're only asking here. Like consider this region, other non-trivial trajectories inside those zero derivative sets. So another way to say it is with our knowledge of the road, consider all those roads everywhere which stay horizontal, doesn't go up or down. Let's now forget about everything except the roads that are inside our neighborhood. If we can prove for those roads that not a single x trajectory sits on those roads entirely, right? Then we've proven that in our neighborhood they are stable. We did not prove anything about other neighborhoods, only about our neighborhood. That is the idea. Okay, now let's try to use it. So back to our example. You remember the example was this: q double dot equals to minus q dot minus sine of q. We've proven that this derivative would be 0 for any q as long as q dot is equal to 0. Now let's consider the set every pair q dot where q dot is 0. Does it contain any trajectory except 0 trajectory? And let us specifically consider this region between minus pi over 2 and pi over 2. Well, it doesn't. It doesn't contain any, right? Because let us consider what's going to happen. We have q double dot, I would call it ddq, is equal to 0. Like q has to be equal to 0, remember, right? Minus sine q, right? That is the what we're discussing. That's what's going to happen. Now, two observations. First, q is equal to constant, right? Because dq dt is equal to 0, right? So for it to be a solution contained inside this set, dq dt has to be equal to 0, right? No. So q has to be constant. Now, ddq, though, ddq would then be equal to minus sine of q. And since q does not equal to 0, right? We're saying it does not equal to 0 because we are not considering trivial solution here, right? So since q is not equal to 0, then sine q is not equal to 0. So second derivative of q is not equal to 0. But if second derivative of q is not equal to 0, how are you going to have a whole trajectory where q dot is 0? So q double dot is not 0, but q dot is 0 everywhere. How is that possible? It is not possible, right? It simply is not possible. It's not a consistent equation. Since dq dt is equal to 0 everywhere, ddq should q double dot also should be 0 everywhere. But it isn't. So there is no trajectory inside the set. All right, so with that, we've proven local asymptotic stability of the system. Now, let us notice something. Why did I put this here? Can someone tell me? Like, if I get rid of this, what would change? No guesses. Just give a guess. It doesn't matter, right? Okay. Okay. I let me explain then. The idea is that there are values of q, such as q equals to pi, which act very similar to q equal to 0, right? So for example, a solution q equals to pi, dq dt equals to 0 is a solution to this equation. So let's look at this. So substitute here 0, here 0, here pi. We get a solution. It is a valid solution. Okay. So there's a valid solution, and this solution represents another alternative. And the problem is that LaSalle principle is not going to prove anything if you don't restrict it like that. because there would be valid solutions outside of the region, right? And for good reason, for good reason. Especially if you consider 2 pi, for example, right? You're not going to say, imagine if this is a pendulum, like I'm going to draw hopefully something that looks like a pendulum, right? Here's a pendulum. And let's say that the angle is between this vertical line and the pendulum itself. First of all, it would be very hard to if you had to prove that this is not a solution, because indeed it can like try to bounce here. It is not a stable solution, but if you put the pendulum perfectly horizontal, it is going to stay there. So you cannot require some kind of stability criteria to prove to you that after some time, the pendulum from this position will go down, right? This is marginally stable, right? It's not asymptotically stable, the solution. But if you consider if what you want to prove is that the pendulum will always go here, back down, it's not going to go back down from this position, right? So this is actually a solution. You cannot ignore it. You cannot use the LaSalle principle to prove that you are going to go from this position to position downstairs. Because if you are perfectly still, you're going to stay perfectly still. Mathematically, not physically, of course. Physically, you have like questions of friction and other stuff that makes it ridiculous. But the mathematically, this is a solution. But even worst is the idea that you can go one like 360 degrees, right? You go like this, like this, like this, like this, like this, like this, right? So you rotate your pendulum like this, right? And you cannot try to prove that for some reason it will rotate back like this and go into your zero solution, Q equals to zero solution. It's not going to do it. It's going to stay Q equal to 2 pi, right? It is asymptotically stable, just as Q equal to zero is asymptotically stable. It is just a question that your number of what do you call it, windings that you did is somehow non-physical. It is just a representation thing. It is actually one solution, one and the same. If you described your state space as some kind of cylinder, you would have returned back to where you came from after this one winding. But we're not going into those depths here. All we are going to say is LaSalle is not going to prove to you that you're going to go from here like this, because it's not the case. You're not going to. So that's why we restrict our region to those angles, right? What I did essentially was, let me try to get rid of as much as I can. What I try to say is basically that there is some kind of region, let's say, between here and here. And no matter where you start in this region, any orientation, you would go downstairs eventually. You can see very conservative. I could have put it much higher. I could have made the region go, like this and like this, and say that all of this would be stable. Of course, there was no point not to. I just chose to prove it for this region. Any questions about that? Okay. Next, another example. So consider a oscillator, again, function of position and velocity, whose dynamics is equals to minus q dot. We choose a Lyapunov function candidate to be kinetic energy of the system. So 1/2 q dot squared. Let's find derivative of this guy. So derivative of this guy would be dv dq times q dot, chain rule, right? dv dq dot times q double dot let me be careful with my color coding. So dv dq dot times q double dot, which happens to be the same as f of x. Now, what would be, again, I'll be careful. What would be this guy? dv dq. Well, dv dq is, derivative of this guy with respect to q. It is 0. So this is just 0. This whole thing. Okay, next. What would be dv dq dot of this guy? Well, it would be q squared, q dot squared, derivative with respect to q, gives us 2q. 2q times 1/2 is just q dot, right? Now we substitute here the, this thing, right? F of x is equal to minus q dot, so we substitute here. So what we have is q dot times minus q dot. So minus q dot squared. That's what we have. Okay. Let's study this function. So first of all, kinetic energy obviously is positive everywhere. Positive everywhere, right? We have to be a little bit wary about the fact that it can be 0 as long as q dot is 0, right? So already something feels off about this Lyapunov function candidate, right? So q is not necessarily does not necessarily satisfy our first criterion, right? Like it's not going to be negative anywhere, but it can be 0 for any q, which is not as long as q dot is 0, right? That's a problem number 1. Problem number 2. So this guy, v dot, is 0 as long as q dot is 0, right? So same situation. LaSalle set, so this set of all states where v dot is equal to 0, looks like this. Q dot equal to 0, that is a set. This set contains a lot of trajectories of the system, aside from this one. For example, q equal to 1 is also a trajectory for the system. So substitute here 0, here 0, solution. Or q equals to minus 2. Again, derivative of minus 2 is 0, second derivative is 0. So again, satisfies this equation. So somehow we get infinitely many solutions. So this does not satisfy LSI principle, does not prove asymptotic stability. In fact, does not even prove marginal stability because of how we chose this function. We have to choose it more carefully because this function doesn't even satisfy the criteria for what Lyapunov function should be like. All right. And in fact, you know the correct answer for this guy, for this thing. Correct answer would be marginally stable. The system is never going to blow up to infinity, but it is never going to asymptotically approach any solution. It's going to come to a standstill somewhere, and it's going to stand there. All right. So not as easy to prove asymptotic stability there, I guess. Right. If any of you want to try an exercise, you can try to prove marginal stability, but find a Lyapunov function, which would be better, which would actually satisfy the Lyapunov criterion. Okay. Any questions? That is the last example. We're going to next topic. Okay. Next, we want to spend a little bit of time looking how this is applied to linear systems. So, of course, it is general. So linear systems is also systems, so we can easily apply it there. For linear systems, there is additional benefit. Namely, we know how to find Lyapunov function. So if you consider x dot equals ax, autonomous linear system, Lyapunov function candidate can always be picked as x times s times x, where s is a positive definite matrix. Well, this is always sufficient. We already saw something like this when we did LQR, right? Okay. Now let's consider how it works. So consider x dot equals ax, v equals x times s times x, which is positive everywhere, zero only at zero, because s is positive definite. Okay. We take time derivative of this function, time derivative of a multiplication of two variables, right? X times sx. So first, derivative of the first variable. Let me color code it a little bit better. Right. So derivative of multiplication of two variables of a product. First, derivative of the first member of the product times the second one, plus the first member of the product times the second derivative of the second member. Right. That is time derivative. Next, what we do is we substitute instead of x dot. I'll show it like this: ax instead of AL, x dot, we substitute ax. So here and here. Right. So when we open the brackets, what we see is there'll be x times sax, and here there'll be x times a transpose sx. So this guy. But we know that v dot should be negative for all x for asymptotic stability. That means that this matrix should be negative definite. That is the definition of what it means to be negative definite. If quadratic form like this is always negative, the matrix in the quadratic form is negative definite. So this gives us a Lyapunov equation. It is slightly more strict. Lyapunov equation goes like this. A transpose S plus SA should be equal to minus Q, where Q is a positive definite matrix. So we want it to be negative definite. So we equate it to some kind of matrix Q, which is a positive definite, and we find S that satisfies this equation. So instead of just proving some kind of finding S that gives us some kind of negative definiteness, we pick a Q, and then we find such S that satisfies this particular equation. So we turn it from inequality to equality. Right, that is called Lyapunov equation. As long as we can find such S that satisfies the Lyapunov equation, we have proven stability of the system. So this is a stability criterion. We can replace eigenvalue criteria with this criterion. We don't have to search for eigenvalues. If it is, for example, very costly, we can instead solve this equation. This equation is pretty easy to solve. There are methods built into mathematical libraries on the very basic level, which solves this type of equations very fast. So it is very efficient, very easy. In fact, there is, as I said, a whole field of control called LMI control, linear matrix inequality, control that uses linear matrix inequalities, which is like half of optimal control, which is based on like in large part based on using this equation. So this equation, it looks very innocent, but it spawns like whole books of methods. Right? So very good equation to use. Questions so far about this one? We have one last topic to cover before we finish. So, if we, but we have time, so please ask questions if you don't understand.
It is like the whole method. If we can find the S, then we prove the stability. And is there is built-in methods to find the feedback control or some kind of other control to ensure that we can find the S, maybe
Yeah,
like
yes,
LQR.
yes. There is. I cannot show it right now because there will be 3 steps to it. 3 steps. So we would derail. But I have slides on that. And at the end of the lecture, we'll discuss what we are going to study in the last 2 lectures. So if you want, we can opt to study this exact point. Basically, yeah, you replace A with A minus BK. You do some changes, and you will get a new equation which would contain not only S matrix that you're trying to find, but another one control matrix, basically. And you'll be able to find K automatically. But this is a stability criterion. That would be control design. You can even check controllability, like derivative of this equation. There is a lot you can do. So it's very powerful. But what I'm showing here is just a stability criterion. That is just stability criterion. Right? Any other questions?
So the matrix Q is just for the definite, and we don't really need its values, right?
We choose this matrix. That's all. We just choose it.
What doesn't change?
Hmm?
What doesn't change?
So
different matrices.
I don't want to sort of like give incorrect answer here. But basically, let's go back a little bit to what we said here, right? This matrix has to be negative definite, right? So we have to find such S that A is negative definite. So if you allow Q to be like a decision variable, basically you can say, just find me some, choose Q to be as small as possible. Doesn't matter how small. And try to find me such S that would satisfy this equality. That is one story, right? It doesn't have to be small, by the way. It can be like just whatever. That is one story.
So we can just set it like identity, and it will be all right.
You can. You doesn't have to be all right, but it how should I put it? Identity doesn't mean simple, right? So it's not necessarily true that you would be able to find that identity would work. It's not necessarily true. Not necessarily true. But
Yeah.
if you simply that's the thing, right? If you don't care about anything other than proving stability, then just being free with how you choose Q is fine. Sometimes maybe you will be able to choose any Q, and there will always be S that will prove the stability, right? Will be able to prove the stability. But in a sense, the intuition behind Q can be read something like this. If you ask for a very big Q, you're asking for a very big eigenvalues of this matrix. So basically, you're not just trying to prove stability. You're trying to prove that you are going to descend along you're going to have a very big derivative here. So, so your Lyapunov function is not only showing that your trajectory goes down, it shows that your trajectory goes down very fast. That can be just the fact that your Lyapunov function itself was very steep, like it was a very big, like function was like a funnel, like it was going up very fast. So it doesn't really say anything about your stability. But if you use this for control design, if you put here, let's say A minus BK, then the choice of Q can be of influence. But yeah.
And then the bigger Q, the more our control, the faster it converts, right?
Yeah. If you did it for control design, but remember, this is just stability check. So basically, if all you care about is stability, then you should be satisfied with any Q that is positive definite. Like you don't have any reason to choose bigger Q or smaller Q. Remember that if you're doing stability check, A is not going to change regardless of how you check it. All you need to is ascertain that A is stable, A is Hurwitz. That is all you need to do. So there is no point of trying to choose Q to be big, small, something else. Any Q that satisfies, that allows you to find S that satisfies this equation is good enough for stability check. If we are going to do control design, completely different story, right? But it's important not to mix those two, right? Stability check is just that. It's like just find something that satisfies this equation. So you shouldn't try to overthink about Q. There is I think, some kind of like subconscious desire to be able to choose not just check stability, but to check how fast we converge, right? But remember, this theory so far said nothing about it. So this idea that you can check how fast you converge would have to be related to something different than Lyapunov's theory that we discussed so far. You can discuss something called exponential stability, where you're saying we'll converge faster than an exponential with a certain coefficient, right? Something like exponential convergence. That's different mathematics. So we shouldn't be tempted to trying to use this the way we discussed for checking how fast we converge. It's just stability criterion. All right. Any more questions? Okay. Let us go to, I think, the last topic for today. We still have a little bit of time. That is discrete systems. So for discrete systems, we can do exactly the same. I will just quickly give you the criterion, Lyapunov theory criterion. It goes like this. If you have a discrete system, next x equals to f of current x, so autonomous system again. It is enough to find everywhere positive function v of x, as usual, 0 and 0, right? Everywhere else positive. Such that the difference between next value of v and the current value of v is always negative. Again, 0 and 0. Then the system is stable. Now, for linear systems, we would also be able to choose v exactly the same as before. Well, let's just look into how it's done. So here's a linear discrete system. Next x equals to x times current x. Lyapunov function is x times s times x. positive everywhere except at 0. Now we need to find what is next value of the function minus current value of the function. So value of the function at the next x minus value of the function at the current x. Well, the way it's done is we take the value of the function the next x, just x times next x on both sides, right? Minus current x, multiplying s on both sides. Now, instead of next x, we substitute a times x. So we get this and this. This value stays the same, right? Now we can open the brackets. And what we'll see is this will be inside the brackets, right? A transpose S A minus S. And this has to be negative definite. So it has to be negative everywhere, like this whole thing has to be negative everywhere except at 0. So it has to be negative definite. And same as before, we, instead of writing is negative definite, we're saying this is equal to some matrix Q with a minus sign, where Q itself is positive definite. So minus Q is negative definite. That's all. And this is called discrete Lyapunov equation. So you can see the criteria in the derivation and how they work about the same. Notice here you don't have to do this trick with eigenvalues being inside unit circle as you had in the eigenvalue criterion. You don't have to think about complex eigenvalues, anything like that. It's quite simple. The heavy lifting was done at the stage where we made Lyapunov theory. Linear case just inherits all those properties. You don't have to prove anything. So the criteria is rather simple. Now, in practice, what you can do is, for example, you can call MATLAB Lyap, and you can see here MATLAB invites you to choose your own Q, right? In SciPy, it is linalg solve continuous Lyapunov AQ. Again, Python invites you to choose your own Q, which you can imagine implies that regardless of what you choose, they will be able to choose something. About that, let me just point out one interesting fact. So let's go back to this equation. Imagine you choose Q, but I come in and I say, okay, no. Let me do one better. I would choose 100 times Q. More strict, right? To which what you can say is, okay, S was a solution to my original equation. Then surely 100 times S will be a solution to this improved equation. Now you can see why I was talking about the function becoming more steep. All you did is just you made the most steep Lyapunov function. Like instead of growing like this, it grows like this. That's all. Doesn't do anything else. So you can see linear scaling like this doesn't actually change anything. Like it is irrelevant here. Whether or not any sort of like scaling won't matter. I didn't prove anything here, so I'm not going to say. But you ask, remember, can you choose identity? No, so MATLAB doesn't mind. MATLAB doesn't mind. So choosing identity doesn't mean that you choose the most easiest function to follow. That's the thing, right? But MATLAB doesn't mind. So go ahead and choose identity. Okay, all right. And that it was like the small introduction to Lyapunov theory. Remember, this is a huge topic. It's going to be you're going to be able to follow it much more closely in a different course. With that, I would stop the recording and we can discuss what we are going to study for the last two classes. We need to discuss it, so please don't leave.